All right. Okay. Hi, everyone. Assalamualaikum and have a good day. So today we continue our lecture regarding this solution to critical section problem using logs, page 42. Yeah. All right. Okay. So software-based solution, such as Peterson, are not guaranteed to work on modern computer, which is current technology. So many systems provide hardware support for implementing the critical section code. All solutions are based on idea of locking, means that protecting critical region through lock. Okay, that's the only option at that time. Okay, so we use this. Okay, like in order to enter that, we put some requirement acquire lock before they enter this critical section, and also after that release, and then do the rest of the section, and then after that repeating. Yeah, all right. So synchronization hardware. So modern machine provide a special atomic hardware instruction to implement locks. So they call atomic, means non-interruptible. Yeah. So two type of instruction they will apply. So test memory word and set a value, and then swap content of two memory words. All right. So test and set instruction. Test and set instruction is a single and indivisible machine instruction known simply as TS. Yeah. And then was introduced by IBM for its multi-processing system, 360 and 370 computer. This is the old-fashioned, a computer. 360 is, I can say, that is a mainframe, the big one. Yeah. So we have this in UTM. Okay, long time ago. Right? But now we are using cloud. Okay, when the cloud came, so we are using cloud right now. Yeah. So this is because very huge 360 and 370. So we put our everything there. Yeah, application, our payroll, our student registration in that mainframe. Yeah. So now we are using different architecture. All right. So in a single machine cycle, it tests to see if the key is available. If it is, set it to unavailable. So the key is a single bit in a storage location that can contain either 0 or 1. So 0 means if it is free or busy. Yeah. So test and set instruction. So definitions. So we use a boolean, whether so true or false. Okay, test and set function names. And then the boolean, so we use the pointer and then we set equal true, so we return the value. Yeah, okay. So this is definition of this test and set function. Yeah, this instruction. So the property of that is actually is executed automatically, return the original value of pass parameter and set the new value of pass parameter to true. And then next, test and set for CS application. So a process which is P1 will test the condition code yeah, using test and set instruction before entering a critical section. So if no other process was in that section, critical section, then P1, yeah, P1 will be allowed, yeah, to proceed, and the condition code will be changed from 0 to 1. Later, when P1 exit the CS or critical section, the condition code is reset to 0 so that another process can enter its CS. On the other hand, if P1 finds a busy condition code, so what it will do, then it is placed in a waiting loop where it continues to test the condition code and wait until it is free. Yeah. So solution using test and set, yeah, function, or this what we call this instruction they call here. Yeah. So first, share Boolean variable which is log initialized to false, and then each process wishing to execute the CS. So here, we put some while test and code at the beginning, and then we put while first, and then they put while and the beginning and here, and after that they put log here. So this is a critical section. Yeah, and then if true, okay. So this is the true, not do anything, correct, and then it just not will do, and then after that enter and the log, and then remain the section, and again repeating until finish. Mean while true, they will keep on looping until infinite loop. Yeah, this one. So figure, this is a figure. Okay, actually mutual exclusion implementation with test and set. We call this function. Yeah. So solution result is busy waiting. And what about the bounded waiting? However, this solution does not satisfy bounded waiting. Yeah. And then read textbook for the solution. So this is stated in the textbook about this scenario. Yeah. Okay. Mutex logs. Previous solutions are complicated and generally inaccessible to application programmers. Whereas designer build software tools to solve critical section problem. Yeah. Simplest tool is the mutex log, which has a Boolean variable which is set initially set, or initially set with this value associated with it to indicate if the log is available or not. However, there is a more robust tool, that can behave similarly to a mutex log, but can also provide more sophisticated ways for processors to synchronize their activity. Okay. So what they are, so this is the SMART4. So SMART4 is a method of visual signaling, usually by means of a flag or lights. Okay. So they introduced this, and then there are used in, for example, in railways, means the raised arm mean track is clear, give a signal, and then lower arm, track is busy and train must wait. Okay, they give some analogy, about the technique we are going to use this. So we are actually introduced this SMART4. So what kind of this? Using the visual signaling through this. So this is the analogy, to explaining about that, about this SMART4. Okay, between foreign navy ship to communicate messages over a long distances. So this is another analogy they use. Okay, all right. This example, okay, this picture, and also this. Yeah. So this one also presenting the analogy, yeah, the semaphore, the concept of semaphore that I try to using. All right. So similar function in OS. In example, it signals if and when a process is free. Not just enter straight away, just give a signal first, and after that, they will indicate that for that function is ready, can be used by a process. So semaphore in OS. Protocol is a protocol mechanism, for task communication actually. Specifically, semaphore are used to control access to share resource, okay, or we call this mutual exclusion. We need to achieve this, otherwise your data will be inconsistent. Okay, when we are sharing, so this is the issue. So finally, we try to use semaphore in OS, Signal the occurrence of an event, allow two tasks to synchronize their activities. Okay, semaphore. Synchronization tool that provide more sophisticated ways than a mutex logs for processors to synchronize their activities. Semaphore, we can use the word as variable s is an integer variable, can only be accessed through or via two indivisible atomic operation when one process modifies semaphore variable, which is s, then no other process can modify it. Okay, modify that variable, which is the variable concurrently. So this one we want to achieve this mutual exclusion concept, and then with a method or function is called PV, the process, and signal call V, and signal, and then call. All right. So definition of wait operation. So we have this wait, okay, and then while s less than or equal 0, and then which is busy, and then s will use the number of s, meaning s0 is less or equal to implies busy means for critical section origin or a process in critical section. So process calling on wait, operation, wait must wait until s bigger than 0. So which is until this value positive. All right. So definition of signal operation. Okay. So we have this as signal. Okay. So the value of signal, they will increase. There's increment on as value to 1. Keep on increasing. All right. So counting semaphore. This is a type of semaphore. Counting semaphore is integer value can range over an unrestricted domain, and binary semaphore means integer value can range only between 0 and 1. This is similar to this mutex log they are using. It's 0 and 1. Okay. So both can implement a counting semaphore as a binary semaphore. Can implement a counting semaphore as a binary semaphore. So this kind of thing. All right. So semaphore usage can solve various synchronization problem, and solution to the CS. Okay, for your information, from my experience, we are using this, even we are using a thread. We can control the thread and then to call this to maintain the consistent value. Otherwise, it will get inconsistent. Okay, so that's why we need this kind of the method and methodology. Please digest this one. That's very important. So a solution to the critical section, create a semaphore which is sync. We have to initialize to 1, and then wait first, this one, initialize, and then we have to this is the critical section part. and then signal to relay. Before we pass, we have to give a signal. Okay, we need to have this kind of thing, yeah, in your code. Okay, so consider P1 and P2 that require code segment S1 to happen before code, yeah, segment S2. Okay, we want this. So we create a sync. Okay, create semaphore sync, which is initialized to 0. And then this is a process 1, and then S1, and then we have a signal sync. And then we have to P2, next is P2, and then wait, okay, wait for the signal, and then after that, start use the what we call this a code segment. Okay, so because sync is initialized to 0, yeah, P is executed only after P1. So this is the we want, even in the thread. So this issue, this one we in thread, even they are all parallel, multiple, and then running concurrent, but we cannot allow, because our target is about the consistent of the data, because we are using maths, everything. So the value must consistent. So that's the issue. That's why we want this flow. We want P1 first, like this, yeah. This one, what we want, because we are programmer, okay. So P1 is executed only after P1. This is that we want, because we are programmer. We want it works like that. It's like a sequence, Yeah, of course. Okay, so now let's say in the case of thread, multi-thread, and then one channel got multi. So how? So this is the solution. All right. So we want this. So when we want this P2 is equal to only P1 has invoked this signal, right? So which is after statement S1. Okay, this. After signal, which is after statement S1 has been executed. This. Give a signal. So mean S1 0 less than or equal 0 implies busy with the critical section or a process in critical section. All right. Okay. So semaphore implementation, busy waiting. So this is type of signal. Yeah, we are busy in the waiting. So must guarantee that no two process can execute this. Either wait and also signal. All right. So on the same semaphore at the same time. This is very important. Yeah. Guarantee. No two processes. Yeah. So thus the implementation becomes the critical section problem where the wait and signal code are placed in the critical section. This implementation is based on busy waiting in critical section implementation. That is the code for wait and also signal. Okay, this is also finalized. This is a technique they are using now. Then we found the solution a couple of years ago. Okay, all right. So we have to adapt this. Okay, but implementation code is short, little busy waiting if critical section rarely occupied. Can we implement semaphore with the no busy waiting? The answer is yes. So the detail you can get from the textbook. All right. Okay. Semaphore implementation with no busy waiting. With each semaphore, there is an associated waiting queue. Is another thing. Yeah. And then each entry in a waiting queue has two data items. First one is a value, which is in integer type. Next is a pointer to the next record in the list. Okay, like this example. Yeah. So two operations. First, we have to block. So place the process invoking the operation on the appropriate waiting queue. And then after that, we have to wake up That's very important. That's why when we use a lot of library, you can see there is open and close, open and close. That's very important one, because this is talking about when we apply something, when you block, you have to wake up. You can see this pair, okay? Okay, this is very important. Okay, this pairing, because otherwise it will permanently, okay, permanently block. So it's a problem. So we need some, when we do these kind of things, so block and after that wake up, yeah? So wake up is to remove one of the processes in the waiting queue and place in the ready queue. So we need this, this scenario. All right, so this is normal when we create something, when you open, because this environment of multi-user, multi-thread, try to imagine that, yeah? All right. And then these are the exercises. I hope you can go through the exercise. I will not explain, but I'll just go through this, yeah? The following code consists of 2 smartphone and also 2 concurrent processes. Assume that these processes run for a sufficient long time under a preemptive scheduler. Preemptive means interrupt or uninterrupt. Preemptive is an interrupt scheduler. Yeah. So this is the struct smartphone, and then this is the variable names. So we have S and B initial value. So got process here. You can see process 1 wait. So yeah, and then we got this another process. Okay, 2 smartphone and 2 concurrent. All right. Okay. So and then so how to fill table 2 and determine a possible output from the printf. Okay. All right. So if you are running in a thread, can implement it. If one by one, I don't see. Okay, we are using the thread. So based on the value of the table to write the sequence. So I need to, okay, this is the process. Okay, they just mentioned about these kind of things. Today is a great. So just go through this, okay? Okay, because this is not what we call this thread. Because thread we got lots of things, but the similar technique that we use for the thread as well. Yeah, thread, multi-thread, so many things, but this is only a single. Yeah, single process. They try to explaining the concept of the smartphone. All right. Okay, please go through this. And also this one they create another possible answer, because why it can be, okay, if we not control properly. Okay, if you are using thread, we don't have this kind of 2 answer. All right. Okay, that's the issue. Yeah. Okay, so this is another example, producer and consumer, where we have the producer function, producer, one is a producer in one loop, or maybe in one last, yeah, different, in the same function, we got producer and also consumer at the same time. One we produce, one is consumed. Okay, all right. So initial value is empty and impute full of 0. Okay, the produce item and wait empty and new tag here. Produce first, and then add next to next buffer, and then signal. So they need to have this, okay, and then through. After that, consume. Consume also, which you can see, wait, and then this one. Wait for full, then wait new text, and remove an item from the buffer, of course. And then after signal, and then signal empty, and then back to the consume. So first, produce, and then after the process of this mutual exclusion, we take law and so on. After that, they start consume. Get that. Yeah, produce and consume. Produce, consume. So only one. Okay. So we apply this even in the thread scenario concurrent. So we need exactly the correct value. Otherwise, it will become what we call this like always inconsistent. Okay, all right. So based on the previous example, fill in the following tables, okay, with the value of those variable used. Okay, these are some exercises. You can go through that. Yeah. So mutate value, and then the producer will start first, since weight is empty, yeah, and then the producer with weight, and then full equals 0, yeah, and then one producer update full one, then consumer proceed with all updated value by producer. Okay, so and check this, and then at the beginning, so for example, initial value mutate 1, so empty equal 5, and then full equal 0. So at the beginning, initial value, next weight, empty is 5, weight, and then currently empty is 4, and then weight, so mutate is 1, so and then minus, and then put 0, yeah, and then next signal, okay, mutate 0, and then increase, can yeah, and then full, okay, and then increase the value full, and then can see. Okay, all right. So next for the consumer, so weight, yeah, full equal 1. So next reduce the number minus 1, and then similar to mutate, then minus 1. Okay, and then after that, signal, okay, mutate equal 0 and mutate equal 1, and then signal, yeah, and then empty 4, and then read increase the number, increase 1 for the signal, which is representing for empty variable, yeah, and then so this is the value what they got after produce. After that, we start use. Okay, use, produce first and then consume after that. Yeah. So incorrect use, yeah, deadlock and starvation. Okay, incorrect use of semaphore operation can produce deadlock. So these are the issue where 2 or more processes are waiting indefinitely for an event that can cause by only one of the waiting processes. Yeah. Starvation, indefinite blocking, where a process has never been removed from the semaphore queue, which it is suspended. So this is the effect when we actually incorrect use of semaphore operation. So we will face this kind of the scenario. We call deadlock or starvation. Yeah. So permanently lock. All right. Okay. Summary: mutual exclusion means to prevent deadlock. So there's a purpose of we have this mutual exclusion. This is a target to prevent deadlock, and then maintain with the test and set with and also signal, including semaphore. Okay, so this all to achieve a mutual exclusion. And then synchronization or synchronized processor using hardware and also software mechanism, algorithm. Okay, we create on hardware and we are using a software. All right. Okay, that's all for chapter 3. See you next on chapter 4.